Hello everyone. In this video lecture, we will discuss some specific organic reaction based on carbon-carbon bond formation. So carbon-carbon bond formation reaction plays a central role in organic chemistry because it enables synthesis of some new compound. So it having new biological and chemical properties. Thus, carbon-carbon bond formation reactions are very important in pharmaceutical chemistry and material science. So, in the first slide, I have shown some typical example of carbon-carbon bond formation reaction in drug synthesis and in natural product synthesis. The top one is the synthesis of a drug which is known as atorvastatin, which reduces amount of cholesterol in the blood. So, during the synthesis of this particular drug, aldol condensation reaction, which is a very well-known carbon-carbon bond formation reaction, is used in a crucial step. As you can see from here, the reaction between a aldehyde and this phenolizable compound. Whereas beta carotene, which is a red-orange pigment found in many fruits and like carrot, it's synthesized by another well-known carbon-carbon bond formation reaction, that is Wittig reaction. As you can see, this aldehyde and this phosphonium lead, which we will discuss later, these two reacts from this beta carotene. Now, from 19th century, numerous carbon-carbon bond formation reactions are known in the literature. And so I have enlisted some of the reactions here in this slide, like Diels-Alder reaction, aldol reaction, which we will discuss in our video lecture, Wittig reaction, McMurray reaction, use of Grignard reagent, Mannich reaction, Ullmann reaction, and the recently very useful in industrial chemically. So Ullmann reaction is one of the oldest reaction on carbon-carbon bond formation reaction, where aryl-aryl bond is formed in presence of copper. And Diels-Alder reaction is one of the most powerful and useful reaction in organic synthesis. Here, a six-member ring is formed from a diene and diene. And the use of Grignard reagent, so in the reaction of aldehydes and ketones, are very well known. So in this our video lecture, we will mainly focus on Wittig reaction and aldol reaction. Now the Wittig reaction is known after German Nobel laureate George Wittig. Professor Wittig and from Germany and Herbert C. Brown from US, they received the Nobel Prize in 1979 in chemistry for the development of the use of boron and phosphorus containing compound. So Wittig contributed to the phosphorus containing compound, and so Herbert C. Brown contributed to the use of boron containing compound with organic synthesis. Now, in a Wittig reaction, carbonyl compound is converted to an alkene in presence of a phosphonium lead. As you can see from the top part, we have a carbonyl compound, we have a phosphonium lead. Lead means opposite charge on adjacent atom. The product is a alkene and the byproduct is triphenyl phosphine oxide. So as you can see, the molecular weight of this byproduct is quite high. So the atom economy is not good for this particular reaction. Now it is important to note that the phosphonium lead is generated from the corresponding alkyl bromide by this reaction. Alkyl bromide with triphenyl phosphine SN2 type reaction. This cation is generated, which in presence of a strong base generates the lead. The detailed mechanism is shown in the slide. In the first step, the lead attacks the polarized carbonyl compound, and this ethane intermediate is formed, which further forms this four-membered cyclic intermediate, which is known as oxaphosphetane. This oxaphosphetane, upon reverse cycloaddition, generates our desired alkene and the byproduct triphenyl phosphine oxide. So as we have discussed earlier, the lead is synthesized from this alkyl halide uh, by using a strong base. So here, this generation of lead is shown for a specific alkyl halide, which is 1-bromopropane. So reaction of 1-bromopropane with triphenyl phosphine to generate this phosphonium salt, which reacts with this strong base in butyl lithium to generate the lead. Now, as alkene is the final product, so stereochemistry in terms of EZ isomerism is important for this particular reaction. So it was observed that when unstabilized lead, means when we have electron donating group in the lead, Z isomer is the predominant product. On the other hand, when electron withdrawing group is present, and the lead is stabilized, and the product is predominantly the E isomer. So the good aspect of this particular reaction is that two things. One is new carbon-carbon bond is formed, and stereochemistry is can be tuned by using either electron donating group or electron withdrawing. Now here are some example of Wittig reaction. The first one is the intramolecular Wittig reaction. So where from a linear static material, a cyclic product is obtained. In the second one, Wittig reaction is used to synthesize this alcohol. The first step is the Wittig reaction. The second one is urylation. Now, aldol reaction is an also important reaction to form new carbon-carbon bond. Here also the starting material is a carbonyl compound. It can be either an aldehyde or can be a ketone. In the first reaction, so we can understand aldol reaction is the addition of an enolate generated from a aldehyde or ketone to another aldehyde or ketone to produce this product. Now, why the reaction name is aldol? Because here in the product we have both aldehyde and alcohol hydroxy group. That's why the trivial name is aldol. So as you can clearly see, this new carbon-carbon bond is formed between this alpha carbon and this beta carbon. Now, if this aldol product is heated in presence of base, this alpha beta unsaturated aldehyde or ketone is generated. This is called aldol condensation reaction. Now, the detailed mechanism is shown here. So, in the first step, the carbonyl compound, which is having the enolizable alpha hydrogen in presence of base, generates this resonance stabilized anion, which is an enolate. Now, enolate in the second step attacks the same carbonyl compound, or if we do a cross aldol reaction, it will attack the other aldehyde or ketone. So, in this step, actually, the new carbon-carbon bond is formed at the expense of this C double bond group. Means C single bond is formed at the expense of C double bond group. In the final step, this beta hydroxy aldehyde is generated and the base is also regenerated. That's why the reaction is truly a catalytic reaction, a base catalytic reaction. Now, As I told, uh, for aldol reaction, necessity of an enolizable aldehyde or ketone is must. So here, two different aldehyde are used. In one case, benzaldehyde, no enolizable protons are there, but here enolizable protons are present. So it will enolize, and this enolate will attack this aldehyde. So the cross aldol product will be similar. Product is obtained in case of this aromatic aldehyde. Uh, Here we don't have any enolizable proton, but here we have enolizable proton. The cross aldol product after condensation with this alpha beta unsaturated ketone. And this last one and this one is the formation of ring after aldol addition and condensation reaction. So in summary, so we have discussed carbon-carbon bond formation by Wittig reaction and aldol condensation. In both cases, the starting material is the either is the carbonyl compound, either it can be aldehyde or it can be ketone, and the final product is an alkene in case of Wittig reaction, whereas say beta hydroxy aldehyde of ketone in case of the aldol reaction.